Okay, so we were actually discussing the classical entropy last time, right? We were discussing the Shannon entropy and its properties. So recall that for any probability distribution associated with any probability distribution, and let's say I goes from 1 to D, you have the associated Shannon entropy, right? So yeah, so I think the last time around we were discussing properties of this. We discussed the binary entropy, we discussed joint entropy, I think, and I think where we left off at was in discussing the relative entropy, right? And I proved to you that the relative entropy is positive. So the things that we've already discussed are so we've discussed the binary entropy, we discussed concavity, and we discussed the relative entropy between two probability distributions. And I think I concluded by showing the positivity of relative entropy, right? So we said that the relative entropy between two probability distributions, and I think I labeled, so I'm not sure whether I labeled this as P of X and Q of X. You can as well call it Pi and Qi, it doesn't matter. But the point is that this relative entropy of Pi with respect to Qi, right? These are two probability distributions, two distinct probability distributions. I might have called them P of X and Q of X last time, where X is the same thing. It's an index that's running. So in which case you will simply say relative entropy between P of X and Q of X, where you can think of these as probability density functions then, or probability distribution functions, right? Okay. So this was defined to be minus sum over I. Actually, let me first define it like this. So it's defined to be sum over I Ti log Pi by Qi, right? So as we realize, this is nothing but minus the Shannon entropy of this distribution, Pi, right? Minus sum over I Pi log Qi, right? If I were to think in terms of a random variable X distributed according to P of X, and then you think of another random variable which is distributed according to Q of X, right? Then this is simply minus the entropy of X as in the one distributed with P of X, right? And then Q of X is another probability distribution, and this is just minus P of X log Q of X, okay? Yeah, I'm not saying anything new. I'm just saying that last time I might have defined with X and I'm now indexing it with I. It doesn't matter. We are anyway talking about discrete distributions. Doesn't matter, right? Okay. So yeah, this was the definition of the relative entropy. And the last time around, we concluded by proving that a key property of the relative entropy, namely that the relative entropy, which is also in the classical case called the KL divergence or the Kullback-Leibler divergence, right, is a sort of distance measure between probability distributions. It tells you how close or how far apart two probability distributions are, right? And this relative entropy is always non-negative, right? So this is a key property of both the classical and the quantum. So today, hopefully, we'll come to the quantum relative entropy as well. So this means that this quantity, yeah, this is why it's easier to write it with x, but anyway, the reason I'm putting this curly braces is to say that this is a discrete set, this is a discrete distribution, right? It's not just pi, it is the probability distribution with probability distribution constituted by P1, P2, etc. up to PD, right? So this is always non-negative, and the proof of this was done last time, right? So I refer to the last lecture for the proof. It basically follows from certain properties of the log function, right? And especially the fact that ln x, the natural log of x, is always less than or equal to 1, right? So the proof follows simply from the fact that ln x is less than or equal to x minus 1 for all x greater than 0. Okay. So this was done last time. Now, I discussed one corollary of this last time. So today I want to discuss one more corollary, which is the subadditivity of the classical entropy or the Shannon entropy, right? So there are two corollaries that come from this. The first one is the fact that, yeah, what was the first corollary? That if I have this distribution I going from 1 to b, right? And if there is some random variable x which takes values xi distributed according to pi, right? Again, I going from 1 to d, then the Shannon entropy of such a random variable, which can take on one of the possible values, or an experiment which has one of the possible outcomes, or an event, rather an experiment comprising of one of the possible events, then this Shannon entropy is always bounded by log d to the base 2, right? And the way to prove this is to take the relative entropy of this distribution, right? Any distribution with respect to the uniform distribution and use the non-negativity of this. Okay, so I don't know if I completed this last time. So this is the first corollary, that the Shannon entropy is always bounded by log d, and so the distribution that achieves the maximum Shannon entropy therefore will naturally be the uniform distribution, right? So this is something I mentioned as a property earlier, but now you see that it can be proved following the once we have shown the positivity, or rather the non-negativity of the relative entropy, the classical relative entropy. So how does it follow from this? So what is the uniform distribution? The uniform distribution is the one which has all entries as 1 by d, right? And there is d of them. So d outcomes or d possibilities all occurring with equal probability, right? That's what the uniform distribution is. So what is this relative entropy? As you know, the left-hand side is basically negative Shannon entropy minus sum over I, pi log 1 by d, right? That's just from the definition of the relative entropy. So you use this first. And then you use the definition of the relative entropy to show that the left-hand side is simply this, but that is nothing but minus h of x minus what? This so what is the second term? The second term is simply plus log d, right? Because sum over I going from 1 to D is 1. And then all of them are just weighting. I mean, it's basically the average of distribution, which I mean is the average of a fixed number, right? It's just log 1 over D. So that's just log 1 over D. Minus log 1 over D is just log D. And then what the positivity of relative entropy tells you is that this is greater than or equal to 0. So then what this means is that h of x is always less than or equal to log D, and that's it. Hence proved. When does equality occur? So note that in the relative entropy case, if and only if Pi is the same as Qi, right? So P and Q must be identical distributions, and only then the relative entropy vanishes. Therefore, this inequality also saturates if and only if Pi is the same as the uniform distribution. Because that's where you started, right? You started by saying compare the relative entropy between an arbitrary distribution for the random variable x and the uniform distribution. Use the fact that this relative entropy is positive, and then you see that the Shannon entropy of this any random distribution, any distribution, is bounded by log D, and equality holds if and only if this equality holds, and this equality holds if and only if these two distributions are the same, which means that this distribution Pi must be the uniform distribution itself, right? So this is the equality condition, and so this is one corollary of the relative entropy. In a sense, we proved a fact which was already known or which was already intuited, but still it's useful to have a formal proof of this statement, right? Okay, the second corollary is the so-called subadditivity of the Shannon entropy. So what the subadditivity property says is that, I think I noted this last time. So if you take two random variables, x, which takes on values xi distributed according to Pi, and let's say y, which takes on values yj distributed according to some qj, right? Then this joint entropy, h of x comma y, is always less than equal to the sum of the individual entropies. This is the subadditivity property. So what is this joint entropy? It is basically the entropy of the joint probability distribution P, or I don't know what you want to call it. So let me call this something else. Let me call this P tilde ij log P tilde ij. So the joint probability distribution Pij, right? So I'm calling it P tilde just to distinguish it from P. Note that this, so the joint entropy is simply the entropy of this joint probability distribution, right? When I have a pair of random variables, then I can have a joint probability distribution over this pair, right? So what is Pij? It is the probability of random variable x realizing the outcome xi and random variable y realizing the outcome yj, right? And so you can write down an entropy for this joint distribution, and that is what this is. So note that it's only in special cases that this P tilde ij will simply factor into Pi qj. When does this happen? If and only if x and y are independently distributed. Or they are independent random variables. Right? So keep this fact in mind. This also will then tell us when this subadditivity is saturated. So similarly, the subadditivity is saturated with equality, right? If and only if X and Y are independent random variables, which means that there is no correlation between X and Y. So now we can prove all of this once again using just the positivity of relative entropy. So the proof now, again, there is a certain relative entropy function which you have to consider, and then use the fact that this relative entropy is non-negative. So consider the relative entropy between the joint distribution and the product of the marginals. What do I mean by product of the marginals? What is a marginal? So when I take p tilde ij and I sum over all j, then I should get pi, right? Which is the probability of the ith outcome for random variable x. Similarly, when I sum over all I should get qj. So these are the marginals, right? But the joint distribution is not in general the product of the marginals. That happens only when if and only if the random variables are independent, right? They are independently distributed. So that's it. You just simply have to consider the relative entropy between the product distributions and the joint distribution, and then set that to be positive. So that is h of p tilde ij with respect to pi qj. This is positive or non-negative. And then what happens? You can expand this once again, and you can show that this left-hand side essentially becomes negative of the joint entropy minus sum over ij p tilde ij log pi times qj, right? But this I can split up as log pi plus log qj. So there's another term here, right? But what is this term? So in each of these terms, here I can sum over the j, right? Because the log only has the pi. So if I sum over the j, then this term p tilde ij sum over j gives me pi. And similarly here I can sum over the I, right? Do the I sum first because the inside the log is only sum over j. It gives me qj. So then I have h of the joint entropy minus, actually it becomes plus h of x plus h of y. I hope you see that. So the reason I'm doing these proofs is so that you get a handle on doing some of these proofs in information theory, whether classical or quantum. Okay. So then this is greater than or equal to 0 is what the relative entropy property says. So then this implies that h of x plus h of y is always greater than or equal to h of xy, and this is indeed the so-called subadditivity. It's simply shortened as SA a lot of times, subadditivity of the Shannon entropy. So what does this say? This says that if I have the joint distribution, then the amount of knowledge I have is less than equal to the amount of information I have about the individual random variables. In other words, what happens with P of P, the joint distribution, is that my uncertainty or how much I uncover, right, is lesser than equal to the sum of the individual entropies, right? So unless, of course, they are independently distributed, in which case the joint entropy has exactly the same information as the sum of the individual entropies, right? So that's just one loose way of interpreting the subadditivity inequality. So these are both important properties of the Shannon entropy, and both of them followed from the relative entropy property, right? The non-negativity of the relative entropy. So finally, I want to also introduce a few other quantities related to the joint entropy and so on. So finally, okay, so the last thing I actually want to talk about is mutual information and conditional entropy in the classical case, and then we move on to talking about the quantum case. So what does one mean by mutual information? So this is a quantity, and the symbol for this that I will use is I. So once again, as the name suggests, you have two random variables x and y. The question is, how much information do they have in common, right? So another way of asking this question is how correlated are x and y? So in a sense, the subadditivity itself tells us something about it. For example, if the subadditivity is saturated with equality, then you realize that these two random variables are not correlated at all. They're completely independent of each other. So when the subadditivity is saturated, then you imagine that this quantity must be zero. Whatever this mutual information quantity is, if it is indeed a measure of correlation between two random variables, then when the subadditivity is saturated with equality, this mutual information quantity must vanish. Right? So let me write this quantity. So sometimes people put a double dot here that's the notation that is used. And sometimes the colon notation is used, right? Both are fine. I think the Nielsen-Chuang book actually simply uses h of xy, but I like to use a different symbol I, and in fact, I'll stick to using this symbol both for the classical and quantum mutual information. Okay, but all three symbols are fine. So you imagine that when, so I was trying to relate this to subadditivity. So you see that when the subadditivity is actually an equality, then this quantity must be zero. And when subadditivity is a strict inequality, which means h of xy is strictly less than h of x plus h of y, then you see that the mutual information in some sense is the quantity that is capturing the gap between this joint entropy and the sum of the individual entropies. So what I'm leading up to is that this quantity is simply the difference between what is the sum of the individual entropies minus the joint entropy, right? So in other words, this is simply the mutual information between, I'm sorry, it is simply the relative entropy. So remember, what was this quantity, right? This was, so it's often useful to visualize the mutual information as a relative entropy like this. So if you notice, this is nothing but this, right? The left-hand side of this relative entropy equation that I wrote down. So it is indeed the relative entropy between the joint distribution and the product of the marginals, right? So if Pij is the joint distribution between x and y, and Pi times Qj is the product of the marginals, then this relative entropy is essentially what is the classical mutual information between these two random variables. And since this is always positive, this is also always positive. So these are all related quantities. The positivity of the relative entropy, the subadditivity inequality, and the positivity of mutual information are all related in this way, right? So, of course, so this, so it's clear, therefore, from this, whatever I just mentioned, that this is zero if and only if x and y are uncorrelated, right? That's what makes it a measure of correlation. In other words, x and y are independently distributed, or they are independent random variables. If they are not independent random variables, and if there is any correlation between x and y, then this mutual information quantity is strictly positive. right? And in fact, it is the difference of the joint entropy. It tells you by how much is the joint entropy less than the sum of the individual entropies, right? So obviously, if these random variables are correlated, then the joint entropy conveys less information than the sum of the individual entropies, and this difference is what is captured by the mutual information. So often in the classical case, people like to draw a certain cartoon picture of these entropies. You can think of this as some kind of Venn diagram, okay? So I will draw two circles, one which is supposed to represent h of x, and another which is supposed to represent the other random variable y. Now, x and y may have some correlation, which means they may have some overlap, right? So what are the different quantities that we've discussed so far, right? So let me draw, I don't know, horizontal lines for one and vertical lines for the other. So this is h of x, right? This is simply the Shannon entropy of a single random variable. Then this is h of y. That's the Shannon entropy of the second random variable. Sorry, I picked a different color. It doesn't matter. But now you see there is a region in between where there is an overlap between these two quantities. What does this region represent? I assume people are around and still awake. So what does this region represent? There I now have checks. Yeah, union means what in this case? Exactly. So this is the region that captures the correlation between these two random variables. So this is in fact the region that is capturing I of xy. Because you see, if they were independently distributed, then there would be no overlap. This would be h of x and this would be h of y, right? And this overlap would be 0. That's when the mutual information is 0. So what the region in between, which has both the dashes and both the horizontal and the vertical lines, that captures for me the correlation between x and y. What about the total envelope? So what about this big envelope here? So that is the joint entropy, right? So this big envelope here, so maybe I'll just draw this with black as a kind of dotted line. This whole thing, in some sense, right? So this captures the joint entropy. And so you now see that h of x plus h of y has something extra. You're essentially double counting this region in the middle to get h of x plus h of y. Whereas the joint entropy does not count that region twice. It simply counts it once, right? So that is why this h of x plus h of y minus h of x comma y, which simply counts this once, will lead me to this overlap region. Okay, so I hope that idea is clear. But now that leaves us with asking the question as to what is this part alone, right? What about just this? So essentially one is asking, what about this region here, which is, how do I represent it? It is h of x minus the mutual information between x and y, right? So let's try to expand that. So you know that the mutual information is nothing but h of x plus h of y minus h of x comma y, right? So then what is this region? This is nothing but the joint entropy minus h of y. So what is this quantity called? This quantity is called a conditional entropy. And what is it telling you? It's saying that from the uncertainty I have about the joint distribution, I'm removing the uncertainty that I have about y, which means that I know something about y. Let's say I know y. right? So this quantity is actually the entropy of random variable x given y. So this is the conditional entropy x given y, and from the picture it kind of makes sense because this is the residual uncertainty that you have about x if you know y. Correspondingly, I can define here this region is the conditional entropy, the other conditional entropy, which is h of y given x, right? So these are all the different entropy quantities that come into play. And this is, I mean, once you know and understand these entropies, you're mostly done, right? As far as information theory is concerned. But just knowing and understanding the properties of these entropies itself turns out to be a non-trivial task, okay? So these are the two conditional entropies that we can define, the h of x given y and the h of y given x. And you can formally define them as well as the joint entropy. So h of x given y is this, the joint entropy minus h of y. Similarly, h of y given x, you can think of it as the entropy of y minus the amount of correlations that x and y share. That also makes sense. You know something about x, and x is correlated to y in a certain way as captured by the mutual information. So you remove that from the entropy associated with y, and that tells you your state of knowledge, or conversely, the state of ignorance about y given x. So this you can work out is exactly the joint entropy x comma y minus h of x, right? So both these conditional entropies are important quantities, and you can also show in the classical case that first of all we said that the mutual information is positive, right? Similarly, you can show that these conditional entropies are also positive. The mutual information is positive, easy to show because it is exactly like a relative entropy between the joint distribution and the product of the marginals. Relative entropy is positive, it simply follows from properties of the log function. And finally, the fact that this is positive comes from the fact that this individual entropy is always less than or equal to the joint entropy, right? Similarly, h of y is always less than equal to h of x comma y. So from the joint, when you remove this, what you're left with is the conditional entropy, right? Okay, so I think this is all that I wanted to discuss. So, I mean, one can go ahead and prove all these statements formally, these last four statements here, but I don't want to get into that. If you want, I'll refer you to a theorem in Nielsen and Chuang, which proves all of the various properties about all these entropies, right? But this is the playing field, basically, right? Now you can go ahead and add a third random variable to the mix, and you can talk about strong subadditivity, you can talk about Markov chains. All of that we will not get into now, okay? We'll recall or we'll use properties from the classical entropy as and when we require it from here on, right? When we're discussing quantum entropies. Okay, so I think with this, this concludes basically my discussion of the classical entropy function. Any questions? So basically, if you understand this Venn diagram, you have understood roughly, at least you've understood all these entropic quantities. Okay, as far as the classical case goes, you will see that very soon that strange things can happen in the quantum case. Okay, so moving on, let's move on to talking about the quantum setting now. So the basic quantity, as far as quantum information is concerned, or quantum Shannon theory is concerned, is the von Neumann entropy. But an even more basic question to ask is, what is the random variable in the quantum case? And what is it that takes on the role of a probability distribution? So what is the analog of the probability distribution in the quantum case? Because what does the Shannon entropy do? It is basically measuring the uncertainty associated with a probability distribution, or it is measuring the amount of information you gain when you learn the value of a certain random variable, which is distributed according to some probability distribution. So in the quantum case, the analog of the probability distribution is nothing but the density operator. Because this rho, this object rho, it captures your state of knowledge, or it is in some sense our state of knowledge about the state of a quantum system. Well, okay, I'm using state in two different sense here, or let me say extent of knowledge. Okay. So what do I mean by this? What do I mean by saying that rho captures the extent of my knowledge about the state of a quantum system? First of all, note that if rho is a pure state, right? If it's a density matrix associated with a pure state, then I know everything there is to know about the state, right? In this case, I would expect that whatever measure of uncertainty or knowledge, conversely, that I use should be zero. Because once I know the state, I know everything there is. I can calculate all expectation values of observables. I know how the state evolves, etc., etc. Right? So once I know that it is a particular pure state, then the uncertainty is zero. So whatever is this entropic quantity that I associate with this must be zero. On the other hand, if rho is truly a mixture of pure states like this, right? Some whatever number of pure states. So this is a mixed state. And the very description of this tells me that I do not know exactly what state my system is in. And this is not a coherent superposition, but it is an incoherent mixture of pure states. So this essentially plays the role. So in the case of a pure state, that essentially the classical analog of that is a delta distribution, right? So this is like a delta distribution, right? But now this is like any other probability density function, which is not a delta distribution, right? And there is indeed one probability measure sitting here already, one distribution sitting here, which tells you how a particular, so remember that density matrices, that's the other thing, you can decompose them in terms of several sets of pure states. There are several equivalent ways to describe a density matrix via several sets of pure states with different distributions. So the same thing could also be associated with another distribution Qj, phi j, and over and above that, there is the so-called diagonal representation or the spectral decomposition right? Which is basically this density matrix can be expanded in terms of the rank 1 projectors associated with its eigenstates or eigenvectors in terms of or weighted by the eigenvalues. So these are all equivalent descriptions of the density matrix, and associated with each of them, you have a certain entropy, right? But how do I really define a single entropy function associated with this density matrix. So first of all, I hope I've convinced you that the density matrix or the density operator is the analog, the quantum analog of the classical probability distribution, right? Or the probability measure, if you will. The density operator or the state, it's what forms a probability measure on our state space, right? And the way to define this entropy, and this was something that von Neumann proposed long before anybody thought of quantum computers or quantum information processing. So this is the von Neumann entropy. So note that it is I like to use a different symbol. Again, different books do it differently, right? I think Preskill, for example, does not use a different symbol. I think he uses H. It depends. It's a matter of taste. I like to use a different symbol because, as you will see, I mean, it's precisely for this reason. You know, I've already kind of told you what's the problem. You have different possible pure state decompositions of the same density matrix. So if I were to associate this classical distribution Pi with the density matrix, that will have its own Shannon entropy. This Qj will have its own Shannon entropy. The lambda i's will have their own Shannon entropy. So what is the entropy of the state? How do I define it? So von Neumann proposed to define this purely as an operator function. Okay, don't decompose this in terms of pure states. What is your rho? Your rho is some positive trace one operator. So remember that the density operator is always a positive semi-definite matrix which has trace one. It is a positive operator on the state space, on the Hilbert space associated with the system, right? So let's say that this is some d-dimensional system. Okay. Let's keep this in mind. So this is defined as negative trace rho log rho. Okay. So that is the definition of the von Neumann entropy associated with a density matrix or a density operator. So it is purely an operator function, right? Or it's a function on the operator space. Oops. So how do I define, so how do I even compute this quantity? So what is log rho? So remember that because it's a positive semi-definite operator, it can always be diagonalized, right? So let's say that this is the diagonal representation or the spectral decomposition, right? This is the decomposition of rho in terms of its eigenvalues and eigenstates. Then what is log rho?
Log lambda I EI.
Exactly. So it is the Hermitian operator whose eigenvalues are log of the eigenvalues of your original Hermitian operator. Remember, any positive operator is Hermitian with the same eigenstates, the same eigenvectors. So if rho has a spectral decomposition lambda I EI, then any continuous function of rho of this operator has a spectral decomposition which is f of lambda I EI, right? So that's how the log is defined. So now if I want to compute this, what is this? What is now trace of rho log rho? So what will this turn out to be? Yes, so I hope you can see that this will simply turn out to be minus lambda I log lambda I. Why? Because both rho and log rho are commuting operators, right? Any operator commutes with a function of itself. They're both diagonal in the same basis. So this product will simply be lambda I log lambda I EI. And then what is the trace? I take the trace in this basis itself, right? Ket EI forms a basis for the space. And so I can evaluate the trace in this basis and I end up with minus sum over I lambda I log lambda I. In other words, the von Neumann entropy of the state is nothing but the Shannon entropy, and this is why I like to use two different symbols for this. This is nothing but the Shannon entropy of the eigenvalue distribution. So this is the Shannon entropy of the eigenvalue distribution. So what do I mean by eigenvalue distribution? So note that the eigenvalues of a density operator, not of any operator, but of a density operator, forms a probability distribution. Why? Because trace rho is 1 implies that sum over I lambda I is 1. The fact that rho is positive semi-definite means that these lambda i's are all greater than or equal to 0. So you put these two things together and you see that lambda I is therefore a probability distribution or a probability measure. So that is how the association happens, that rho becomes a probability measure on the state space. And so there is in this, well, whether discrete or continuous, there is an association you can make from rho to this probability distribution of its eigenvalues. And you can associate a Shannon entropy with that eigenvalue distribution. And that is what you then define in some sense as the von Neumann entropy of the density matrix. So that is what motivates this definition of negative trace rho log rho, because it evaluates very nicely to the Shannon entropy of the eigenvalue distribution. Okay. So this is the fundamental definition of the von Neumann entropy. So now, of course, we go ahead and look at various interesting properties of the von Neumann entropy. So as with the classical entropy, it is often useful to immediately go and look at the relative entropy, okay? And the relative entropy function will again be positive. So before I move on to properties of this, I want to talk about the quantum relative entropy. Maybe before that, I should just talk about some limiting cases, just to give some intuition. Oops. So what are the limiting cases that I want to talk about? So the first limiting case is, of course, when rho is a pure state. So what is S of rho in this case? That is negative trace psi psi log psi psi, right? So you realize that this is nothing but it is as if I have an eigenvalue distribution with just one non-zero eigenvalue, right? Because I can always complete a basis with any, starting with any state of the space, any pure state. So it's as if I have a single eigenvalue, right? And so it's like a delta, so the associated, it's like a delta distribution as far as the eigenvalue is concerned. So it's like there is only one non-zero lambda I. So that then essentially becomes, it is like your limit x tending to 0 of x log x. So that is 0, right? So this is like a delta distribution in lambda I. So I have basically lambda I is 1 for some I and 0 for all the remaining i's. So let me say lambda 1 is for I is equal to 1, and for all I not equal to 1, the lambda i's are all 0, right? That's what it means. So like in the classical case, this will evaluate to a 0 entropy scenario, right? The second limiting case will be the case where rho is a maximally mixed state. So in d dimensions, this is nothing but the state I by d, where I is the d cross d identity matrix, right? So in other words, it is like saying that, so remember that any orthonormal basis can be used to realize the identity matrix like this, right? If I take any orthonormal basis, right, and I sum over all the projectors onto the different elements of the orthonormal basis, I should get the identity matrix. That is the completeness property. So it's as if all your eigenvalues are 1 by d, right? So this is the analog of the uniform distribution in the classical case. So this then is nothing but the uniform distribution. The eigenvalue distribution is the same as the uniform distribution, and so this von Neumann entropy is going to be the same as the Shannon entropy of a uniform distribution, which is log b. Okay, so, and of course we will again prove using the relative entropy property that this is the maximum value that the von Neumann entropy can take for a d-dimensional space. If I have a d-dimensional Hilbert space, if my quantum system is of d dimensions, then the maximum von Neumann entropy that any state can attain is log d. The minimum that it can attain is 0, which is of course attained for any pure state in the space. So we can go ahead and prove this now using the relative entropy. So how does one define the quantum relative entropy? It's exactly analogous to the classical case. So I will now simply define. So again, there we were comparing two probability distributions. Here we are going to compare two density matrices, two density operators or two states, right? So like in the classical case, the relative entropy was a measure of distance between probability distributions. Here it will turn out to be a sort of distance measure between states. So in the earlier part of the course, you already saw one distance measure, namely the fidelity, as a measure of distance between states. And that was useful in characterizing the action of the effect of noise, the action of an error correcting code, and so on. But from an information theoretic point of view, it is often more useful to compare the information content of two states or compare the entropies of two states. And that is what the relative entropy does. So this is defined again as trace rho log rho minus trace rho log sigma. Okay. So, well, even in the classical case, whatever I'm going to say is possible, but in the quantum case, you have to be even more careful about defining this. So if, so in some sense, this definition holds so long as sigma is within the support of rho. Okay. So if the zero eigenvalue space of sigma has some intersection with the support of rho, then this quantity can blow up. So this is a technicality, and again, if you're interested, I can talk a bit more about this, but let me just note that this can be infinite if so let me say the kernel of sigma. So the kernel means the space associated with the zero eigenvalues. So obviously you note that there is a log sigma sitting here, right? So if sigma has 0 eigenvalues, then there is a region where this can blow up, right? Because as you approach in the if in the standard definition of just the von Neumann entropy, you have the balancing act, you have rho log rho, right? So in the limit, rho log rho is still finite, but here you don't have sigma log sigma, you have rho log sigma. So unless that vanishes, this can blow up. Do you understand? So whenever this log sigma has 0 eigenvalues, and that space of 0 eigenvalues of sigma has some overlap with the support of rho, then this can blow up. Okay, so essentially the way one takes care of that is by artificially setting this to be 0, right? So, or you declare that this is well defined so long as the support of sigma lives within, no, you want it the other way around, the support of rho lives within the support of sigma, right? So, yeah, I think I said that correctly. So long as the support of rho lives within the support of sigma, then you've ensured that this non-zero, that you only have overlap in the region where rho and sigma have non-zero eigenvalues, right? And whenever you have 0 eigenvalues for sigma, you don't go into defining this. Or whenever you have 0 eigenvalues with some overlap with the non-zero eigenvalues of rho, then you do not really define that, right? Or in other words, at those points, you simply say that the relative entropy has become infinite. The same problem exists in the classical case also, where you have two probability density functions, P of x and Q of x, and you have a log Q of x sitting there. But anyway, like I said, we didn't visit that explicitly so much there. But let us stick to this kind of a definition. By and large, you know, the density matrices that we'll consider will not really have 0 eigenvalues for the most part. They will have well-defined support on the entire space usually. So typically you will find that support of rho is equal to support of sigma is the complete space, right? Because there will be no 0 eigenvalues by and large. So these are some corner cases, but this is how you address those corner cases. Okay, fine. So with that spiel, let us go into understanding this relative entropy quantity. So once again, the key property of this is the positivity of the relative entropy. So this positivity of relative entropy has a name associated with it for some reason. It is called Klein's inequality, which basically says that the relative entropy between rho and sigma is always non-negative with equality if and only if rho is equal to sigma. So we will try to prove this in what remains of today's class. I think I have another 10-15 minutes. So how do I prove this? So let us start by doing spectral decompositions of this. So note that this definition of the relative entropy has a certain asymmetry about it, right? Because S of rho sigma is trace rho log rho minus trace rho log sigma. If you want to make the analogy with the classical case, remember we wrote there, we could write the relative entropy as minus h of x. Similarly, this becomes minus S of rho minus trace rho log sigma, right? That is the definition. So let us expand. So consider the spectral decomposition of rho and sigma. So that's where you start typically. So let's say that rho has a bunch of eigenvalues. So let me call this P and Q, because then you will kind of recover the classical probability distribution language. So I is a set of eigenstates associated with rho. And then with sigma, you have another set of eigenvalues, Qj, associated with a different orthonormal basis, J. Okay. If you want, you can put EI and FJ, but just understood that they are different bases. Okay. So from the definition, you see that this is minus, oops, there's no minus here, it's just sum over I log Pi minus, now I can choose to take the trace in either basis, right? I can take the trace in the basis in which sigma is diagonal, or I can take the trace in the basis in which rho is diagonal. Note that it is not at all necessary that rho and sigma need to commute. Okay. So I is one orthonormal basis and J is a completely distinct orthonormal basis. They are two separate orthonormal bases for the space. Okay. I choose to take the trace in the eigenbasis of rho so that this becomes sum over I Pi log sigma I, right? Well, I can write this as rho log sigma I, but essentially now I can further reduce this. So as you can see, I'm just working towards getting back to a classical distribution, right? So then this becomes sum over I Pi log Pi minus sum over I and J. I have Pi, I have Qj, because this I expand in its diagonal basis. And then I have this overlap, inner product Ij mod squared, right? This is what I have as far as the second term is concerned. Oops, should be log Qj, sorry. Okay, so nothing new so far. So now let me pull out the Pi outside, right? So I'm basically trying to get to a form of a classical relative entropy function here. So then I have log Pi minus sum over J log Qj, the overlap between I and J. Okay. So let me now redefine this quantity. So I want to define a quantity, so which is okay, so this, let me define this as a matrix, capital Pij, and then you notice certain things. So when I sum over I of this quantity 1 to b, what do I get? It is as if I'm expanding. So what is this quantity? It is the overlap function between the two orthonormal bases. And when I sum over I alone, it is as if I'm expanding ket j in the I basis, right? It is basically the the norm of ket j itself, right? So that is 1. And so also when I sum over j going from 1 to b of this capital Pij, that is also 1, because in one case it will simply be so it will simply be like this, right? So I have the j can be expanded as sum over I inner product ji I, right? So when I take modulus squared of this, it's as if it's all these expansion coefficients. So that is nothing but the overlap of J with itself, or in other words, the norm of J. So in one case, it is inner product of J with itself. In the other case, it's the inner product of I with itself. So both of these are 1. So if I define this Pij as some matrix P, whose ijth entry is this overlap mod squared, then you notice that this is a matrix which is what is called doubly stochastic. It's a doubly stochastic matrix, means the sum of the rows and the sum of the columns is 1. And what is more, these entries are all positive semi-definite, right? So what this means is when I take this sum over J log Qj times Pij, you see, it's as if I'm mixing the log Qj, I'm weighting all of them by some coefficients Pij, and these coefficients are all positive semi-definite coefficients, and they are elements of a doubly stochastic matrix. Okay. So now if you use the fact that this is a concave function, the log function is a concave function, then I can take these inside, right? I can take these, I'm essentially weighting the log function with these coefficients, the Pij's. So I can take them inside, and what I will end up having is a less than equal to sign, where I will have log of sum over J, Pij, Qj. Okay. And this Pij, Qj is as if I am modifying this probability vector Q by the action of this doubly stochastic matrix Pij. And so this is, if I define this as some Rj, right, that itself forms another probability distribution. Okay. So let me state this clearly. So that I'm defining Rj as sum over J, Pij, Qj. So if you imagine Q as a vector, right, with Q1, Q2, etc., Qd, okay, and imagine this Pij as a matrix, right, with entries P11, P12, etc., P1d, PD1, PD2, etc., PPD, where each entry is simply that overlap function. So if this is P2D, that will be 2D mod squared, right? In the two different bases, by the way. Sorry, I mean, it's a bit of abuse of notation, but these are two different bases that one is talking about, and one is talking about the overlap in that. Okay. So this is a matrix. This is this doubly stochastic matrix that I wrote down here. And now I'm saying that I'm acting this vector Q with this matrix P. So obviously that's going to give me another vector R with entries R1, R2, etc., RD, right? Where each Ri is nothing but sum over J, Pij, Qj, correct? So that is what this is. But what is this vector R? Because I'm modifying one probability vector, because I'm taking one probability vector and I'm acting on it with a doubly stochastic matrix, what should the output be? What will the resulting vector be? Anybody who has done standard probability theory? So the output will also be another probability vector. This is like what we do in quantum physics, where you take one normalized vector in a d-dimensional Hilbert space, you act on it with a unitary matrix, then the output is also another normalized vector, right? The unitaries are norm preserving, so they map states to states. In a similar way, the doubly stochastic matrices are the norm preserving transformations here. They are the ones that preserve the normalization, the fact that the sum should be the RJs must sum to 1. Sorry, this should be Ri. Okay, so you can check this, huh? So you can check this, and in particular, you can check that sum over I Ri is 1. Just like how sum over little qj is 1, sum over little pi is 1. This capital Pij, which is the matrix of the overlap between one matrix to another, one basis to another, is a doubly stochastic matrix. So under its action, this qj must go to another probability vector rj. So I've done two things here. One, I have defined another ri. Oops. Here also should be ri. I've defined another Ri such that that is also a probability distribution. Second, I have used here, what have I used here? I have used the concavity of the log function to say that sum over j, some number times log qj or some coefficients times log qj is less than or equal to log of the sum, right? Sum of coefficients times log is less than or equal to log of the sum. So this is concavity property. All right, so I hope you are all not completely lost, but essentially till here was straightforward. We just expanded the two states in their own orthonormal bases, and then I pulled out the common, the log pi outside, and the second term, right, I had this. So basically, I'm trying to map this to a classical relative entropy function. I'm there as far as the first term is concerned. For the second term, I want something like log of another probability distribution. So how do I get to that? First, I use concavity of log to take this inside the log, okay, to take the sum inside the log. And then what is inside the log, which is this sum, Pij, Qj, I define that to be Ri, and I show that it is a probability distribution because the coefficients that are weighting the sum are drawn from a doubly stochastic matrix. Okay, so with all of this put together, you see that S of rho sigma is nothing but, what was it? It was plus sum over I pi log pi minus sum over I and j pi, capital Pij log Qj, right? That's what it was. Now this second term, I've basically shown without the negative sign, I have shown that it is less than or equal to. So with the negative sign, it is greater than or equal to minus sum over I pi log Ri, where Ri is nothing but sum over j Pij Qj. Okay. So in other words, this is nothing but sum over I pi log pi by Ri. In other words, this is the classical relative entropy between two distributions pi and Ri, and this is always positive semi-definite. So the fact that this is positive semi-definite, the classical entropy is positive semi-definite, then tells you that this quantum relative entropy is always positive semi-definite. Now, what about equality? So I assume that you followed so far. Okay. So with this, I will conclude equality statement. So in the classical case, you know that from the properties of the classical relative entropy, you know that equality is achieved if and only if pi is equal to Ri. right? So what does that mean? In this case, actually, there are two inequalities. There is one inequality here, which came from the concavity property first, right? So that concavity property must first be saturated with equality. And for that to happen, each of these Pijs must be equal to, so what should happen? So you need that Pi is equal to Ri, but Ri is sum over J, capital Pij, Qj, right? So this must be equal to Pi. And not only that, so this is one inequality, one equality condition. And the second equality condition, for the concavity to hold, for the concavity to have saturate with equality, you need these Pijs to be all, each row of this matrix should have just one non-zero entry and everything else should be zero, right? So this concavity thing saturates if and only if Pij is a permutation matrix. That's what it means, right? If this matrix is such that in every row and every column there's only one non-zero entry, it need not be the diagonal, it can be anywhere. That's why it's a permutation matrix. But all the other entries can be zero. That is when the concavity inequality will saturate, right? So both these things should be satisfied. So you notice that Pij is this overlap, right? So if this has to become a permutation matrix, which means for every j, there is only one I, where this inner product is non-zero, and that non-zero value is exactly 1, then that means, so this is a permutation matrix. Implies that J is simply a permutation of the I basis, right? Or in other words, rho and sigma are diagonal in the same basis. So this is the first condition, that rho and sigma must be diagonal in the same basis. But if they are diagonal in the same basis, and this is just a permutation matrix Pij, then for every j, there is only one non-zero I. So there is a Qi which is equal to Rj, which is equal to Pi. So the second condition then means that, so this is what 2 implies, that rho and sigma must be diagonal in the same basis. But then 1 implies that Pi is equal to Ri, which then should be equal to Qj for some j, right? For every I, there is some j such that Pi is equal to Qj. So what that means is that rho is simply equal to sigma, because their eigenvalues are also the same. They are diagonal in the same basis and their eigenvalues are also the same. So rho must be equal to sigma. Okay. So yeah, this takes some time to wrap your head around this quantum relative entropy and its positivity. In the classical case, this was a very straightforward proof. It simply relied on the fact that the log function satisfied some property, or the log function is always bounded from above by x minus 1 or something. But in the quantum case, it's much more involved. You first have to map the quantum relative entropy to the classical relative entropy, and that is where the positivity comes from. And then the equality comes from two conditions. One, that the matrix between the overlap matrix between the two bases, this must be a permutation matrix, which then means that the two density matrices that you're comparing are diagonal in the same basis. And secondly, these two distributions must be the same. That's what the classical condition tells you. So that in the quantum case implies that Pi is equal to Qi is equal to Ri essentially. So then that means rho must be equal to sigma. So the summary is that the relative entropy between two quantum states is always non-negative with equality if and only if rho is equal to sigma. Okay? So I stop here and we'll continue tomorrow. So this concludes the proof of positivity. Please go over this again, and if you have any questions, we can discuss tomorrow. Okay? Any questions now? Yeah. Yeah. Sorry, can you speak up, Neelkant? Yeah.
I have a couple of questions.
Yeah.
Ma'am, so wait, this might be a silly question, but this rho and sigma, are we considering them to a density operator over the same Hilbert space? Because you have taken a dimension of I and
Yeah.
dimension of J to be the same.
Right, right. No, it is not at all a silly question. Like I said at the very beginning when I defined the entropy, that the definition is a bit tricky because it could happen. Okay. So the way I will rephrase your question, it's not so much about whether they're defined on the same space as whether they are both, whether they both have the same support, right? I could define two density matrices on the same space, but while rho has support on the entire space, maybe sigma has non-zero eigenvalues somewhere and it has only support, some limited support. In that case, it's not very well defined, right? Because there are zero eigenvalues for sigma. And when I take trace rho log sigma, I will end up with infinity. So I assume typically in all this that the support of rho is either equal to the support of sigma or is within the support of sigma. Okay? Very simplistically, yes. I assume that they are both full rank on the same Hilbert space. Because that is the most common scenario that we will encounter as far as information processing is concerned. So yes, in a very simplistic sense, that's what I'm assuming. But a more precise answer is that I'm assuming that the rho support of rho is either equal to or contained. So I think I wrote it just contained. Is either equal to or contained in the support of sigma. Okay?
Yes. And now, where you presented that to use the concept of W stochastic thing, right?
Yeah.
So this Q vector you wrote.
Yeah.
That is in J basis.
So sorry. Okay. Now when I say vector, I actually mean a real d-dimensional vector. So this is a real d-dimensional vector. This is just a probability vector. I'm not writing a quantum state. That's why I didn't put a ket or anything. It is simply the vector of eigenvalues of the density matrix sigma.
Yeah.
It's a classical probability vector.
Yeah, I had.
Can you speak up? Sorry. Yeah.
Because I thought this W stochastic matrix is in a way changing the basis whether Q is getting charged.
Actually, that's a very good observation, and indeed it does. Okay, I didn't mention that, but it very much does.
I was writing it, so Q was
Yeah.
in J basis, then Pij, then sum over J. So R was in I basis.
Yeah, so this matrix Pij, since you asked, let me mention this, but I didn't want to confuse everybody. So you see this Pij, which I defined like this, right? So what is this? This is actually, it is not so much a basis change as a matrix of basis overlaps, okay? Why do I say it's not a basis change? So what does a basis change mean? It means that I must have a matrix, a D cross D matrix act on I and change it to J. Actually, it may be better if I put E sub I and F sub J so that it becomes clear that I'm talking about two different bases, okay? So there is a unitary matrix that has to act on I, EI, and change it to FJ. Actually, FI, normally that's what we say, right? So this is how we do basis change. Correct?
Yes, ma'am.
So this Pij is not doing that. You understand? Rather, it is computing what is the overlap between one basis and the other. So one simple example of this could be, consider one basis to be the 0, 1, our standard example, and the other basis to be plus minus. Now, what is the unitary that changes back and forth between this? You know the answer, that's the Hadamard. But what is Pij in this case? So Pij, this matrix, or what does the matrix P look like in this case? It is a 2 cross 2 matrix with entries 0 plus mod squared, 0 minus mod squared, 1 plus mod squared, 1 minus mod squared. Right? So what is all of this?
1 by 2. 1 by 2.
Whereas what is the Hadamard?
1 by 2.
Correct?
Yes.
So these are not the same. This is the basis change matrix. But this is a doubly stochastic matrix because you see its rows and columns all sum to 1. This is the matrix of overlaps between the two bases. Okay?
Yes. Yes.
So you see a doubly stochastic matrix has all positive entries which sum to 1, right? And these are the class of matrices which transform probability distributions to probability distributions. That is something we did not really study, right? We have always been interested in state transformations, and there what matters is that the modulus squared of these things be positive. Not so much that the entries themselves be positive, but the modulus squared of the entries must satisfy certain properties. So even the unitarity property, where the sum and the sum of certain things add up to 1, it is the mod squared of the sum which adds up to 1, not just the entries themselves. Right? So that's the difference. So the unitary matrix is the quantum analog of the doubly stochastic matrix, which maps states to states in a norm-preserving way. Okay? And the doubly stochastic matrix, the other way to think about it, is a classical analog of the evolution matrix. If classically you're interested in probability distributions evolving, then the class of objects to consider are the doubly stochastic matrices. Okay? Yeah. Okay. Yeah, good. I'm glad you asked the question, so I got to clarify this better. Okay. Any further questions? If not, I'll see you all tomorrow then. Tomorrow's class will be at the usual time. Okay.